Okay, for our next set of topics, we're going to cover adding both categorical and continuous predictors into the same model. So let's think again about our previous example of these foundational ideas. Okay, so we thought about, we're interested in predicting the price of a new home in the Provo area. We Google average home prices, find out that they range widely, but they average about $375,000. Okay, so we thought about, what would be the best predictor, and we talked about the mean, and then I had that question of sort of what external information would help you make a better prediction. So if you knew something about, instead of you're talking about the entire area of Provo, which is a pretty big geographical area, you thought if you had information about which neighborhood it was in. If you had information about the features of the home, how many rooms, the square footage of the home. If you had knew about the school system that they're in, or the specific schools that people go to, and so on. If you could use that information, then you'd be able to make a better prediction about what the specific home price is going to be for that next home. Okay, I also want you to think about what kinds of problems might you run into when taking into account the external information. Okay, so how are you going to express something like neighborhood in a regression equation? Because up to this point we've used mother's last weight, which has been a continuous variable that's measured in pounds. But neighborhood doesn't have a numeric value, so that's something you might want to consider, is that we might need to make some adjustments in how we deal with some of the variables that we might be interested in when making a prediction about a home price. Let me remind you about the data that we're using and the variables that are in it. Okay, and a couple of the things that we're going to focus on in this go around. Initially, it's going to be this race variable. Okay, and we'll talk about that because that's a categorical variable, and we're going to need some specific procedures to be able to deal with that in a regression model. Okay, we're going to take a quick detour into types of variables. The distinctions I'm going to make regarding types of variables might be a little bit different than what you've run into before. So you maybe run into the nominal, ordinal, interval, ratio distinction. And those are fine. That can be a useful distinction, but that's not what we're going to focus on in this class. The first kind of variable we're going to talk about are what we're going to call measured variables. Okay, the idea here is that observations typically can or do take on a large number of values. So even in your data set, you don't have a large number of values. If you can imagine pretty easily a large number of values, that's usually a good indication that we're talking about a measured variable. And the second thing is that the numeric values represent either greater or lesser amounts of a variable. So the bigger the value, the more you have of whatever variable you're interested in, the lesser amount you have. And so you can think of something like weight or height or money. Typically, the way we're going to deal with things like depression and anxiety symptoms, we're going to treat as numeric values. Again, where if you have higher values on the anxiety scale, that typically means you have higher anxiety symptoms. A second type of variable is our count variable, and the key thing here is it describes the number of something. And they're often occurrences of an event. So some of the research that I collaborate on is people who have problems with drinking, and so problems that might occur when they've had a lot to drink. So all the way from hangovers to drunk driving to getting hospitalized, those sorts of things. And so we might count the number of problems they have post drinking. That would be an example of a count variable. Also doing some what's called meta-science research, where we're studying sort of the citation of particular kinds of studies. So the number of citations would be a good example of a count variable. The other thing to know about a count variable is they only take on non-negative integer values. So the lower bound of a count variable is 0. You can't have negative counts. And then they go on up into the integers, so you have 0 or 1. You don't have For example, in the citation example, you don't have half a citation. You either have a citation or you don't. Or you have 2 or 1, but not 1.5. A second or another kind of variable is a categorical variable. And here I'm going to make the distinction between ordered and unordered. Ordered categorical variables are where there's categories, but there's some ordering to them. Okay, so where maybe you ask a question about a symptom, say anxiety symptom, and you just say there's no symptoms, there's moderate, and there's high. And so those might be your 3 categories. There's an ordering to them where moderate's more than none and high's more than moderate, but we don't necessarily think there's an even separation between none and moderate and then moderate to high. Unordered categorical variables are pure categories where there's no order whatsoever. So things like gender, major at school, race, those sorts of things are going to be pure categories, and there can be lots of levels of those categories. There can be lots of distinctions. Sometimes there can just be 2, and so a dichotomous unordered variable is just a special case of the categorical unordered variable where there's only 2 values. So if you have treatment condition where there's treatment versus control, that would be a binary dichotomous unordered variable. So take a minute and pause this and see what you think for each of the types of variables here. Okay, so typically I'd say the number of previous statistics courses is a count variable. Fear of statistics, if we're measuring it reasonably continuously, would be a measured variable. Age would typically be a measured variable. Your thesis dissertation advisor would typically be an unordered categorical variable. Research interests, same thing, unordered categorical variable. Okay, income, you might have that being a measured variable. And then spouse's height, typically a measured variable. Okay, why do these matter? Well, you can think about the different kinds of models that you're going to run into statistics, and often which one you use will depend on what kind of variable you have as your response or your outcome variable, and what kind of variable you have as your explanatory variable or your predictor variable. So here on the left, I've got 6 different models, okay, and the first 4 from a t-test, ANOVA, ANCOVA, and regression are all when you have a single measured response variable. So they're all expecting that your outcome is continuous. What the difference is between t-test, ANOVA, ANCOVA, and regression is what kinds of variables are possible as the explanatory variables. For a t-test, it's just a dichotomous categorical variable, just comparing 2 groups. For ANOVA, you can expand that from not just dichotomous, but you can have unordered explanatory variables. Okay, in ANCOVA, analysis of covariance, you're going to have a mix of unordered explanatory variables as well as some measured explanatory variables. And then in regression, you get to combine all those things. So regression is the most general approach of these things. And so you can do a t-test in a regression framework. You can do an ANOVA style analysis in a regression framework and so on. And that's because they're all part of what's known as the general linear model. When you have different kinds of response variables, such as dichotomous response variables, then you're going to use logistic regression. If you have count, you're going to use a Poisson regression or negative binomial regression. But because those are regression models, the type of explanatory variable is going to be the same as it was in regular regression. And these models are what are known as the generalized linear model in the sense that they've been generalized to accommodate different kinds of outcome variables like dichotomous and count.